Okay, lesson 212. This lesson is a little bit of a departure from the lessons we've done so far. Number one, this one comes entirely from your IEC manual. We're not in the electrical systems book at all for this lesson. But furthermore, this one we're going to get into introduction to AC theory, and I'm not going to touch on places of assembly. But so this one is a lot different because it's a lot less code oriented and install oriented, and it's really a theory lesson here. And there's a ton of good stuff. I'm not going to attempt to touch most of it in this short video, but um, sort of a word of warning or caution. Don't get hung up on the details and of all this different stuff. Not to say any of it is any less important, but they get very into detail. Quite frankly, it's going to go over some people's heads, and to some degree goes over my head. They venture into almost engineering to a degree. Um, but I'm going to try to break down what I think is kind of the most important concept we have to start with here. Okay, and that's simply, what is alternating current? I mean, we talk about it all the time. Do we know why it's called that, and what exactly is alternating here, right? So alternating current. The book gives a couple words of definition here. But in AC current, a basic generator consists of a magnetic field, an armature, slip rings, brushes, and resistive load. So here we see sort of a broken down model of a generator. So your armature is going to spin in between the pole piece here, as they call it. Basically, as this thing spins through these magnets, essentially, they create an electric field. Okay. When a conductor is moved through the magnetic field, a voltage is induced in the conductor, and as the armature rotates through the magnetic field, a voltage is generated in the armature. This causes current to flow through the armature. So, essentially, if we think back, we know electricity is basically the transfer of free electrons from one atom to the other in the conductor, in the copper. So the copper atoms are actually exchanging electrons. Um, Again, we're getting pretty far down the rabbit hole here, but let's look at how this generator actually works. And this is where the alternating piece comes in. So let's take this same generator here and just look at it from sort of a straight on view, a two-dimensional view, right? And we're going to throw up here next to it an actual sine wave. Okay, so this is what they call a sine wave. It essentially goes equally up and down, and it's very symmetrical. And essentially, this wave is measuring our voltage as it goes up and back down to zero. This is our zero voltage axis here, It goes into the negative and then back up to the zero again. Okay, that's actually what our the rotation of the generator causes in our current, and it alternates from zero to peak maximum to zero again to peak minimum back to zero. So let's look at what that looks like as the generator spins here. So we're at 0 degrees in our rotation. That's our starting point. Notice we're equally far away from this pole of the magnet and this pole. We're right in the middle here, right? So at 0 degrees, so here we are again at our 0 degree axis on our chart. As we rotate to 90 degrees, right? We've just rotated this thing 90 degrees. See that again, back to zero. We rotate 90 degrees. Notice that now we are as fully engaged with this pole of the magnet as we possibly could be at 90 degrees. So again, if we check the sine wave, we're at the 90-degree point and we're at our maximum voltage, our peak positive voltage. Let's continue the rotation here, right? Down to 180 again. Let's look at that one more time. We go from 90 down to 180. What do you notice? Well, again, we're equally far apart from either pole. What do you know? We're back down to the zero voltage axis, right? And you can kind of probably imagine where we're going next. But again, let's rotate around to 270. Now we're as fully engaged with this opposite pole as we were when we were over at 90. But this time it's opposite. So now we're on sort of the negative side of the axis here. And we'll bring the whole thing back around with one more rotation back to where we started in the rotation and back to 0 volts on our graph here, right? So that's what we refer to as one cycle. Okay, so let's just kind of look at this thing all together and let it repeat itself, right? This is what our generator is doing, obviously a lot faster. And the graph shows what our voltage is doing. It's actually going up, back to zero, back to negative, and back to zero. So that's that alternating piece that we see. Is it's positive, back to zero, down to negative, back to zero, and it just keeps cycling through like that. And you can see the generator spinning accordingly, right? Here's one other animation I pulled. It may make it clearer for some of you. Then again, maybe not, but this really shows the same thing. We have sort of this rotation here, and this arrow indicates the intensity of whatever we're measuring. In our case, it's going to be voltage. And you can see it's kind of just going up and down, alternating, and it's moving in a consecutive fashion. It's not getting faster or slower. The wave is the same distance apart. One peak from one valley to the next peak is all the same distance, right? Again, I don't know if that makes it any more clear or not, but that's a different way to look at it. The other thing that's important to remember in all this is, if you guys recall, we everything in America operates on 60 cycles per second, or 60 hertz, which means, one cycle, if we go back here a little bit, is basically, so here we're at 0, we go to 90, we go to 180, we go to 270, back to 0. That's one cycle. So in America, our electrical systems do that 60 times in 1 second, 60 cycles a second, otherwise known as hertz. So cycles per second is hertz. So we have 60 hertz. In Europe, they operate on a 50 cycles per second operation, but and this is showing us a quarter second. So this is actually 15 cycles. So here we start, we go up, back down, and back up. That's one. So they do that 15 times in this graph. Multiply that by 4 to give you 1 second, right? So we're going to do that 60 times in 1 second. And then to add one more layer to the puzzle here, so we just looked at kind of one phase of electricity. And in all of our installs, we have single phase, which uses 2 phases of electric, or 3 phase, which naturally uses 3. So the trick there is that those spinning armatures need to be out of phase with one another. So in a 3-phase system, as they show us, we want them to be as far apart from the next one as they can be. Mathematically, that's going to be 120 degrees out of sync with one another. If we have a single phase system with only 2 hot legs, they'll be 180 degrees out of sync with one another. But that's what gives us different hot legs, different phases, is because their sine waves are out of sync. One thing to I want to throw in here is when solar electricity was big years ago, well, not a couple years ago. Solar creates DC current, changes it to AC current, and feeds it back into the grid, right? A grid-tied system. How do they do that? How can we make power and put it back on the same system and not have a short? Well, the key is that they use an inverter, which goes from DC to AC, but that inverter will match up the sine wave. And it's very particular. Voltage drop is a major issue in solar installs. Because of that, we can't have voltage drop because we need to make sure we're matching up sine waves, because we're creating power and putting it right back on that same phase. So our sine wave must match there, right? So again, that was very, what was that, 9 minutes of very brief intro into AC theory. I hope a lot of that sounded familiar and maybe was a little repetitive. But again, I think we need to have that basic understanding before we can even begin to talk about the concepts in the book here. But again, spend the time, read through it. It's all great stuff. Don't get hung up on the details. They get very in-depth. So don't beat yourself up if it's a little tough going there. But stick with it, and we'll get through it.